What you're looking at isn't a complex fractal, and it wasn't drawn by a spirograph either. It's something much simpler, yet infinitely more fascinating. It's a shape made entirely of perfectly straight lines, intersecting at precisely calculated angles. Look closely right here. There are absolutely no curves in this web at all. And the craziest part? This entire geometric structure is controlled by just two simple numbers, n and d. By changing these, we can generate an infinite variety of mesmerizing patterns. Just a slight tweak to either value completely transforms the geometry, building entirely new, overlapping webs right before your eyes. To understand how this works, we first need to step away from our standard XY Cartesian grid and enter the beautiful radial world of polar coordinates. Here, instead of moving over and up, every point is defined by its distance from the center, called r, and its angle of rotation, theta. This brings us to the classic mathematical Rose curve, defined by the remarkably elegant equation r equals sine of n times theta. The number n is what dictates our petals. Notice how the shape dramatically changes as n increases. At n equals 2, we see 4 petals. At 3, we get exactly 3. Go up to 4, and it jumps to 8. 5 gives us 5, and 6 explodes into a 12-petal flower. You might have noticed a strict mathematical rule here. An odd n gives you exactly n petals, while an even n doubles it, resulting in 2n petals. So how do we get from this smooth, continuous rose curve to our straight line masterpiece? This is where the Maurer Rose comes in. We take our base rose and introduce our second parameter, the angle d. Instead of drawing the whole curve, we only drop a pin at every d degrees. Imagine walking along the boundary of the rose, but only stopping to leave a marker at precise, regular intervals. One step, one pin. Another step, another pin. We just keep stepping by d degrees. Remove the underlying curve, and the geometric illusion reveals itself perfectly. A complex curve built entirely from rigid lines. But here is the mystery. Why do some values of d look incredibly boring and sparse, while others look absolutely spectacular? Notice how setting d to 60 degrees barely creates anything at all. It traces a few lines and immediately stops. But slightly tweaking it to 71 degrees gives us a gorgeous, densely packed web. The secret to this contrast lies in a classic concept from number theory, the greatest common divisor. If we take our boring 90 degrees, the greatest common divisor with 360 is 90. This means our line only hits 4 unique points before it loops back and repeats the exact same path. But for 71 degrees, the greatest common divisor with 360 is just 1. In math terms, we say these two numbers are co-prime. Because they share absolutely no common factors, our line is forced to bounce 360 times before it ever repeats, giving us that maximum density and the most beautiful pattern. Let's see what happens if we smoothly increase d. As the angle changes, the shape breathes, continuously evolving between simple, sparse loops and complex, dense webs. Watch how the lines overlap and cross each other, forming transient, star-like patterns that quickly dissolve into chaotic threads before finding mathematical harmony once again. But wait, what if d isn't a whole number? What if it's an irrational number, like pi? Because pi is irrational, it shares no integer ratio with 360. The line will never perfectly close. It will just keep tracing new, unique paths forever. The exact same thing happens with the golden ratio, creating a dense, endlessly non-repeating thread that will slowly fill the entire screen if we let it. And we don't have to stop at just sweeping d. If we lock in a prime angle for d and instead sweep through fractional values of n, the petals themselves begin to morph and multiply in beautiful, unexpected ways. It's like watching a digital flower bloom, fold into itself, and sprout new leaves in a continuous, endless dance driven entirely by pure math. So, from a simple sine wave, sampled at a specific angle, connected by straight lines, emerges an infinitely complex web of geometry that tricks the eye. Mathematics is beautiful. What values of n and d do you think create the best looking shape? Try it out and let me know in the comments. If you enjoyed this visualization, make sure to subscribe to the channel for more deep dives into beautiful math animations. See you next time.